Okay, so as instructed, as these were handed out yesterday, some of you may tune in at a later time. As you can see, we're moving on to our next section. We started to balance chemical reactions, and that's what a lot of you, well, everyone has handed in as of today. And that the idea of balancing equations, that does not stop. You continue to do that process even when you classify these reactions. So with these, would you like to classify them first or balance them first? Okay, so here are your choices. Okay, so we'll go ahead and balance them first as requested. So the aspects that we look at here is, are we making something? Oh, that's right. You said you wanted to balance them first. Okay. So how many of you still write these out, each element or molecule that you have below the arrow? Or you just do the math in your head?
Math in the head.
Okay. So one way to look at that would be, all right, we've got two hydrogens here, and since hydrogen is a gas, we got two hydrogens over here because it's by itself. Okay? We've got an SO4 molecule here with a -2 charge. We have an SO4 molecule over here, also with a -2 charge. One calcium, one calcium. Did anything change from one side to the other?
Yeah. No.
What changed?
Calcium with the sulfate.
Okay? So what we see happening here is we had sulfate was with hydrogen. Now we've got sulfate with calcium. And the best way to look at these is if you see something all by itself. Okay? And the reason we're jumping ahead to that is because you correctly said that nothing had changed. So the last thing we would need to do is classify that. And since you have a lone metal all by itself and a replacement had taken place, just one replacement, that makes this a, ran out of room, we've got a single replacement. Okay? The equation down in the blue. Okay? We see a lone gas all by itself. We see that here. We also see that here and also over here. The idea behind that is to illustrate that when you see gases and halogens, but not the noble gases, when they're by themselves, that we want you to put that little 2 behind it because it is diatomic. Okay, so upon looking at this, these come in pairs. Okay, we've got 5 oxygens over here, so the best thing to do is get that up to an even number, and when you do that, you double it. And upon doing so, the only way to do that is to do what to this compound? Okay, so upon doing that, you distribute that through the entire compound. 2 times 2 gives you what for phosphorus?
4.
So we've got 4 over there, and how many over here?
1.
Okay, so that means we have to have a 4 here. Okay, then again, we distribute that 2 through the entire compound. 2 times 5. Then over here, again, these come in pairs. If we got 10 over there and only 2 here, we're going to want to put a 5. Okay? So then upon doing this, okay, looks like we got 4, 5, 2. And then we're taking one substance here, and making something a little more complex than what we started with. And when that happens, nothing's being replaced, nothing got broke down, okay? We're not burning anything because when we look at this, phosphorus really isn't a combustible material, I believe. So then taking these and making something is a synthesis reaction, or SY. Okay? Then our next one down, we have a hydrocarbon, hydrogen and carbon here, okay? And if you have a hydrocarbon that's combining with oxygen, giving you carbon dioxide and water every time, okay? You correctly said is a combustion reaction. Now, in this case, what is the best thing that you can do for yourself upon balancing this reaction? There's something that we pointed out to you earlier this week. Okay? And the reason we do that is because this number is even. Okay? Now that's not always going to be the case. From prior knowledge, if we look at this, this is what we call an alkane. If this is a different functional family called an alkene, that gets to be a little more tricky. Okay? So, nonetheless, we want to double this right away. So 2 times 6 for carbons gives you what? Okay? We've only got one here, so we got to get this up to a 12. Okay? Our carbons are now balanced. Okay? Let's not worry about the oxygens. Let's move on to our hydrogens here first. 2 times 14 gives you 28. And we've got 2 here, so we're going to need 14. Now we've got the hydrogens balanced, the carbons balanced. Then the next thing we need to do is our oxygens. We've got 12 times 2 and 14 times 1. 14 times 1, 14. 14 and 24 gives you what? So then 38 divided by 2. Okay. Okay. It's going to write it above the arrow, but I'll put it over here. CB for combustion. Okay. I'm going to erase some of this content here just to give us a little more room. Okay. Yeah, I'll just leave that up so some of you can maybe get caught up if we're going a little too fast. All right, our equation in the purple here, okay? And the reason that we see this wrote out, I always like to go back and review some of the concepts that we've learned over this semester. When it comes to balancing out a compound, not the equation, but balancing out the compound, start with which charge, the positive or the negative? Start with your negative charge. So what we see happening here is oxygen has a charge of negative what? 2. Okay? It's negative 2. And then how many of them do you have? 3. Okay? So that's a total of negative what? 6. Negative 6. Okay? So aluminum is in column 3, so it's got a charge of plus what? 3. Okay? So 3 times 2 would give us positive 6. Now, these are already balanced out for you. The compounds, the molecules, all of that. But sometimes you have to finish the reaction. That's why it's important to review these concepts that we've learned. Okay? So this has a neutral charge, and then so does this oxygen. But nonetheless, we still want to balance that. Okay? We have an odd number here. These come in pairs. So the best thing to do is what? Double your oxygen. Okay? We're going to double our oxygens here or here. Okay? Because remember, this is an odd number. We need to make that an even number. Okay? So therefore, 2 times 2 gives you what? Okay? And then 2 times 3 for oxygen. Okay? So we've got 2 here, so we need to put a 3 there. Okay? So we've got 2, 4, and 3. All right. So what do we see happening here? We see a compound here and its separate parts over here. So it must have been broken apart. So that is decomposition. And I should have asked for all involved in here, are we going too fast? Because one of the advantages here that I would like to think that we have is if you have the same teacher for physical science as this class, we're reviewing a lot of the same concepts, but we perhaps just go a little faster. Okay? All right. Go ahead and erase this one. Okay. So why don't you work on balancing this yourselves rather than, and chances are, if you're shouting out answers, they're probably right. But let individuals who are working on this and trying to follow along, let them do that task first. So I will go ahead and hit pause here for just a moment and put some more examples up on the board. Okay, so do we have an answer for that yet, or do we need a couple more moments?
For what one? The bottom one?
For the very bottom one.
We need a couple minutes.
Okay. Okay, so now we're going to go ahead and proceed with this bottom equation. So when we look at this, whether you choose a metal or your polyatomic ions, you just need to have a place to start. Usually we suggest starting with your metals, but that's not always the case. So you tell me, do you want to start with your polyatomic ions or your metals?
What about the metals?
Okay, so then cobalt is a metal, and so is lithium then. So we'll just go from left to right. We've got 1 cobalt here and 2 cobalts on this side. So then just by trial and error, let's just put a 2 here. See once what happens. Okay? So then that balances out our cobalts. But then what does that do to our chloride ions? Gives you 6 because that 2 has to be distributed all the way through. So if we have 6 chlorides on this side and only 1 over here, what would we do? Put the number 6 here. Okay? Then we've got our cobalts are balanced, our chlorides are balanced, but we don't have our lithiums or our sulfates balanced. So should we choose to put a 3 here, because that's our only choice, because by putting a 2 here, that's not going to help us because that would only get us up to 4. 2 times 2 would just give us 4. But 3 times 2 would give us 6, and that's what we have over here. Okay? So then distribute this 3 through the entire compound. We have 1 sulfate ion right now, but we distribute that 3 through the entire compound, and that's how many sulfates? That's how many sulfates? That's 3 sulfates. Then how many sulfates are on this side? Inside the parenthesis, we just have 1, but since that 3 is on the outside, that gives us 3 more. Okay? Because one of the last thing I want to do before we start tackling some of this is, remember we said, go by your negative charges. Okay? Chloride has a charge of negative what?
1.
Okay? Cobalt, in this case, has a charge of plus what? It's going to be plus 3. Okay? Because 3 times 1 gives you positive 3. Negative 1 times 3 gives you negative 3. That now adds up to 0. Okay? Sulfate has a charge of negative what? Negative 2. And then lithium has got a charge of plus what?
1.
Plus 1. So 1 times 2 gives you positive 2, negative 2 times this whole molecule now. Okay? This whole molecule has a charge of negative 2. Does this add up to 0? Yes, it does. Okay? So the charges will not change. We just want to illustrate that those compounds are balanced before we start. As you can see, that is not the case up here because we had this compound split apart here and split apart here. So when we see two compounds split apart from one another, something's getting replaced. In this case, the cobalt got replaced by the lithium, but on this side, okay? So we see two switches that have taken place because lithium is now with chlorine over there and the sulfate ion is with cobalt, but on that side. How many of you remember this from physical science? I would expect that almost every hand goes up. How many of you remember this? Okay? So if you're having problems, you've got to take initiative on your own. Because as we proceed forward, we still have, I understand the semester is going to wind down fairly quickly, but we have some difficult material coming between now and the rest of the semester.
Like
Because
what kind, like,
stoichiometry.
what's that? You wanna give us the problem?
Yeah, show us a stoichiometry up there once. Gotta get.
Okay? If you had 18 grams of cobalt chloride, how many grams of cobalt sulfate are produced?
3,
No.
4,
No.
7.
I don't know. I can't tell you that
How do you know we're not right?
because it's a 4-step problem.
I just did it in there.
Didn't we already do 4 steps this year?
We did.
So is that what you use?
Also, I don't like that.
But you had done composition stoichiometry. What that meant was if you had 18 grams of this compound, you would calculate, okay, how much of those 18 grams is chloride or chlorine? That is just remaining with one substance.
So you gotta do it.
Reaction stoichiometry means you're taking one compound and converting it to a different one to see what you're going to make. And you had done that in physical science. We just did the calculating together. This year, however, you are responsible on your own for making those calculations. But we haven't gone far enough to figure that out yet. Okay? So, again, if we have problems balancing these reactions, you just can't do stoichiometry. Oh, well, you don't want to use the word can't. Well, okay. It's really, really difficult to do stoichiometry then. Okay?
Are you pretty good with it?
Well, I hope so.
You still find it a little challenging?
Yeah.
So why we learn it?
So why are you learning it?
Yep.
Because 1, it's in the content standards. 2, you decided to take this class, correct? I didn't tell you to take this class. Oh, I did. When's that? Okay. And with the final that we have for this exam, the very first day, we made it very clear. We said, there's a way that you can get out of taking this final. Use the door. But you all made the commitment to stay here. So we're all in it together. Okay? All right. Sorry?
You're gonna be a stoichiometrist.
Yeah. It's gonna be a stoichiometry.
I hope not.
Why not?
Cause that ain't even a career.
No, you'd be just a general chemist. You wouldn't be a stoichiometrist. At least not to my knowledge. Okay. Can we erase this?
Yup.
Yep.
Okay? All right. Yes, sir. All right. Sometimes we tell you what the equation is, and you have to be able to finish it. Okay? So, the reason we know this is single replacement reaction is because we have one lone metal over here. So, we're not too concerned about the magnesium right now because it doesn't tell you the charge, but I would expect that each and every one of you can tell me the charge of magnesium.
+2.
And that's correct, but why is it +2?
Because it's second column.
Because it's in the second column. Okay? Now, I wouldn't expect you to be able to tell me what the charge of iron is right away unless you're told what the charge of the hydroxide ion is. Okay? So in this case, one hydroxide ion has a charge of negative what?
1.
Okay? And because there's a 3 outside that parentheses, this whole molecule has a charge of negative what?
3.
Negative 3 now. Okay? So that must mean if there's only one iron atom, this has to have a charge of +3. The reason that you might want to do this first is so that you can balance this out on this side. Okay. So you choose how you want to do your switch first or your lone metal by itself over here first. Well, if we're going to do the switch. What would we write here then?
Mg and OH.
Mg and OH. Now, before you proceed, remember the charges will not change. Okay? So with that being said, you can go ahead and copy them over here. And notice that does not add up to 0. Okay? So again, you laugh all you want, but we are going to see this. It's just a simple mistake. Simple mistakes can be corrected. Okay? And it's important that we do two things. One, try to learn from our mistakes, and two, try not to repeat them. Okay? So, if this isn't correct, how can we fix that? Okay? Now that compound is now balanced. And then what do we have left?
Your iron.
Plus iron.
Just have iron.
Mg, lone metal.
Okay?
+3.
Do we need that though?
No.
No, you don't need that. Because it's by itself.
Just simply uncalled for.
Okay? So,
Put a 2 in front of the iron on the left. Can you stop disrupting?
when we look at this, there's only one place that you can start. And that is with which of the elements or molecules up there is not balanced.
Your hydroxide.
Your hydroxides are not balanced. These come in pairs. This is an odd number. So how do we get this up to an even number for our OHs? You're going to multiply it by 2. That gets distributed through the entire compound. So we have 2 irons. You have to put a 2 here then. Now your irons are balanced. Distributing this through the entire compound, 2 times 3 is what? Okay, so you got to put a 6 over here.
A 3.
Put a 3 there.
Put a 3 in front of that manganese.
And then you have to put a 3 here. Okay?
Now you're balanced.
Okay.
C plus CO4.
What happens when things, whether it's animals or whether it's molecules or whether it's compounds, when they decompose?
They break up.
They break apart. Okay?
They get
So, I like to ask this question. In your estimation, what is probably the number one mistake that students are going to make here?
They're gonna
Okay, so let's start with this first. Where is this going to break apart?
Right in the middle.
Okay, so right here. Okay, so what is going to happen on this side? If this is where it breaks apart, which it does, that gives you C or carbon plus what?
CO2.
We got a 4 there, so should we bring that over here?
Right, cut that in half.
Why would we cut this in half? That doesn't make any sense. When it's by itself, it's what? This is perhaps one of the most common mistakes that we're going to see, is not remembering or forgetting that those are diatomic. Okay, so we've got 4 chlorides over here and only 2 over here.
So you're gonna get 2 in front of that overall.
There we put a 2, and that's it.
And then all it is 1, 1,
1, 1, 2. Okay? Now, this next equation, what is probably the number one mistake that students are going to make?
That diatomic.
That diatomic molecule. Okay? So we see a single replacement reaction here, just like what we did up here. So, do you want to deal with the compound first or the metal first? Okay? Do the compound first. All right. So, if this breaks apart, which it does, okay?
LiCl.
So then the replacement, this lithium, replaces this hydrogen, but on this side. Notice, why are we not, let's say, worried about the charges like we did up here?
Because they're already.
All 3 of these have a charge of what? Okay, whether it's positive or negative. They all have the same number. Not the same charge, but just the same number. So -1, +1. That adds up to 0. Then H2, because gases are diatomic. Okay? So, to finish this then, we've got 2 hydrogens over there and only 1 over here. Okay? Now your chlorides are balanced, but we've got 2 hydrogens. Or 2 chlorines, excuse me.
So put that in front of the yield. Now you need a yield.
2, 2, 2, and 1. Okay? Now, I just want to do, well, we can come back to this one. Okay, you have to tell me, are we going too fast?
No.
Okay, then this bottom number, notice we've got more subscripts down here than any of our prior examples. Are any of these subscripts going over to that side for sure?
No.
We've got 1, 2, 3, 4. We've got 4 subscripts. So of them 4 subscripts, which ones may be going over to that side?
All 4s.
Okay? So when you say all the 4s, why do these 3 4s have to go over there?
Part of the compound.
Because it's part of the compound. It has to follow it over there. Okay? So, if this is a double replacement, which it is, you can base what you know from a single replacement where it breaks apart. That would be here and here. Do you prefer that we go through these charges first like we did up here?
Yep.
Might as well.
Okay? So go by our negative charges. Phosphate has a charge of negative what? Okay? The ammonium ion. So +1 times 3 is +3. And each phosphate has a charge of -1, or excuse me, each phosphate has a charge of -3, and we've got 1 of them. Okay? Sulfate has a charge of negative what? And since there's nothing written down here, okay, because if we did this, you would have to presume that this is not written correctly, because this either has a charge of +2 or +4. If we said this is a +2, you would have 2 times 2 giving you 4. So we would know that that's not written correctly. Okay? So with that, we can presume that this has a charge of +2, which it does. The charges will not change when these switch and go to the other side. Okay, so do you want to start with your tin or your ammonium? Okay, so it breaks apart. We've got NH4, and then let's just start with that. It's going to bond with the negative ion here, but on this side. Okay, so you said the sulfate. So both 4s have to come over here. Now,
We need 2 ammonium.
okay, so if this is +1 and that's -2, because the charges will not change, that does not add up to 0. Okay, so we've got 1 ammonium ion, but we must need 2 of them. Need parentheses and now, if you are confused on where we're getting these numbers below, you can always find your least common multiple. We've done that in physical science. 2 divided by 2 gives you 1. 2 divided by 1 gives you 2. Okay? So what do we have left over in this compound?
Your phosphate.
You got your tin and what?
Can I go put my water?
Yes, sir.
What?
Charges do not change. That does not add up to 0. What is your least common multiple? Okay? So what is 3 divided by, not 3,
Double 3.
right, 6. So what is 6 divided by 2?
3.
What is 6 divided by 3?
2.
Okay. So getting back to this reaction stoichiometry, okay? Again, what you may have done last chapter is if you have 18 grams of ammonium phosphate, what is even the percentage of hydrogen in that compound? You're only dealing with one compound. Reaction stoichiometry might say if you have 18 grams of this compound, how much tin phosphate can you produce? That's why we say if you are having problems balancing these reactions, it just makes doing stoichiometry that much more difficult. Okay. All right. So where do you want to start? Ammoniums, tins? Okay, so are your ammoniums. You've got 3 on this side and only 2 over here. So these come in pairs. We need to get this up to an even number. So we're going to try 2. 2 times 3 gives you 6. Okay, so then 2 times 1 for phosphates gives you 2. They're already balanced because we've got 2 of them over here. If we put a 3 here, okay,
Now you have 3 tins, which is even with the other side.
2, 3, 3, 1. Okay. That is where we will conclude and hand out your papers. Some of you already have them from yesterday. It gave you the directions on here that if you're gone today, please tune into this channel. And hopefully you found it as valuable as the students sitting in here have as well. We hope. That's all we can do. All right. So we will catch up to you next time.